Good afternoon. Let's begin. Section 4.4. Indefinite integral. 5.4? Yes, 5. Sorry. Indefinite integral and the net change theorem. So I want to begin with reiterating the two parts of the fundamental theorem of calculus that we derived last time. So fundamental theorem of calculus, part 1, requires what? It requires a definition of a function g. Okay, and it tells us that g prime of x is f of x. For the purposes of this lecture, I'm going to rewrite exactly the same thing by using a slightly different notation. So instead of g prime, I'm going to use ddx. Okay, and for g of t, I'm actually going to use its definition. From here's 0 actually, not 0, a of x, f of t dt, and that's equal to f of x. So this is exactly the same thing as here, except I'm using a different notation for the derivative, and I'm including the definition of g for g. But now if you look at this, you will see... question?
Quick question. What does FTC mean?
Oh, fundamental theorem of calculus. Okay. So what happens to the function f on the left? So we take the function f, then we integrate it from a to x, and then we differentiate it with respect to x. And in the end, what happens to it is nothing, right? We take f, we integrate it, we differentiate it, and it remains f. So this shows you that, in some sense, the operation of differentiation is opposite to the operation of differentiation. Integration and differentiation are opposite to each other. You do something to the function f, and then you undo it. Okay? So this is what this thing says. Okay, now there's more. Let's look at fundamental theorem of calculus, part 2. So what does it say? The integral from a to b of f of x dx is f of b minus f of a. Again, I'm going to rewrite it slightly differently, because what is f? F is the antiderivative, so f prime is equal to f. So when I rewrite this theorem, I'm going to, in the integral, instead of f, I'm going to insert f prime. So I have f prime, okay, of x dx is equal to f of b minus f of a. And now look, it's also telling us something about the relationship between differentiation and integration. What happens on the left? I take the function capital F, I first differentiate it, then I integrate it, and I end up with f again. Okay? So again, you can see the duality of the two operations, differentiation and integration. So these are the two parts of the theorem rewritten in this beautiful way. And they also motivate a different notation for an antiderivative. So you probably know it from before, but we'll say here that we have a new notation for the antiderivative. So we say that the indefinite integral f of x dx equals f means that the derivative of f capital is f lowercase. So our old definition of the antiderivative was to start with function f lowercase and say that f capital prime of x is equal to f, so f is the antiderivative. Now instead of saying that, we're just going to use this notation. Okay? I will illustrate this with a few examples. So, what is the antiderivative of secant squared x dx? Right? Exactly. All this is doing is asking us to write down the antiderivative, and we know it from a table. So this is just tangent x, and we have plus c. Questions? Okay. Then another one, sine x dx. Okay, this is the antiderivative of a sine. We know what that is. Negative cosine plus c. Okay. Another one, I don't know, say k. K is a constant. What's the antiderivative? Kx, very good. Plus c, right? I don't know, x to the n. We could rewrite the whole table like this, right? X n plus 1. This is our old table of antiderivatives that we started this course with. This was the first thing that we reviewed, right? But now we can write it in this notation. And the notation is very similar to the integral. And I'll go over the differences in just a second. So I'll give you another example. For instance, x squared plus 1. Okay? Do you remember what this is? Arctangent. And let's do another one. A to the x. So this is a general exponent, not e to the x, but a to the x. So the formula is slightly different from your regular natural exponent. Okay? And so on. Okay? So now I want to go over the differences between definite integrals and indefinite integrals. So let's make a table. So first, notation, right? Notation. Notation is almost the same. It's like this here, and here we have A, B. So this is how you can tell. If you see the limits of integration, that's a definite integral. If you don't see the limits of integration, that's an indefinite integral. And the meaning is completely different. So what's the meaning of this? This is just the antiderivative. What's the meaning of this? We know what that is. That's the, if the function is positive, it's the area. Otherwise, it's a net area or signed area, right? Okay. And now a couple of differences. So is that a function? This guy, absolutely. The answer of this, the result when we evaluate the indefinite integral, is going to be a function of x. In fact, it's going to be a function of whatever variable appears here. If I had f of z dz here, that would be a function of z. F of t dt, that would be a function of t. Here, this is not a function. It's a number. It's an area, right? A number. It's not going to depend on x or whatever else I have under the integral. That's a silent variable of integration. It does not appear in the answer. And finally, the additive constant. When you evaluate this, we say plus c. When we evaluate this, we have a definite number, and there is no additive constant. No c. Okay? So there are some similarities, there are lots of differences, and when we evaluate these, we always need to know these. Why? Because of the fundamental theorem of calculus part 2. To evaluate an integral, we need the antiderivative. Okay? So we're going to need the antiderivative to evaluate the integrals. And so I'll show you several examples. But before, do you have any questions on this? Okay. So, very good. What's my first example? Okay. Sorry. So, when we are asked to evaluate this, what is this? As you can see, there is no limit. So this is an indefinite integral. We need the antiderivative, so the answer is x cubed over 3 plus c. It's a function of x. It has an additive constant. Okay. Now, from 0 to 1, this is now a definite integral, and we can use the result from here to get the answer. So we just say x cubed over 3 from 0 to 1, and we already know it's 1/3. Okay. So this demonstrates that we know, by knowing the indefinite integral, we can evaluate the definite integral quicker. Right? We know what to do. The next example is like this: sine theta over cosine squared theta. Okay, d theta. Again, no limits. Therefore, it's an indefinite integral. So it's going to be a function of theta. Right? So the answer is going to be the function of theta. Look at the table. You don't find this. So the only thing we can do at this stage, we don't know any rules of integration. We can only simplify. So we simplify this. We say sine theta over cos theta times 1 over cos theta d theta. And this already looks like something. Okay? Because this is tangent theta times secant theta. That must ring the bell. What's the answer? Secant. Absolutely. Secant theta plus c. Okay? So that's the indefinite integral. Now, to do the same thing from 0 to pi over 4. Okay? Sine theta cos squared theta d theta. All I need to do is I'm going to use the antiderivative that I just found. So I put down secant theta from 0 to pi over 4. Okay? So what's the cosine of pi over 4? That's cosine of pi over 4 will be 1 over square root of 2. Secant is square root of 2. So I have square root of 2. Cosine of 0 is 1. And that's it. Okay? I cannot simplify this. And there's no additive constant. Questions? Okay. Very good. One more example on this. Three t squared plus t squared square root of t minus 7 t squared dt, right? So this is an antiderivative, again, that is not in the table. By the way, I have to make a disclaimer. This is not an exhaustive table. You can find the table in your book, right, in this chapter. I only gave you some examples. But no matter how hard you look, this is not on the table. So we have to simplify. So I'm going to divide through by t squared. I get 3 plus square root of t minus 7 over t squared. dt. And now I can do something. So this is now an antiderivative. It's going to be a function of t. And I can do it term by term. So I get 3t plus t 3/2 over 3/2 minus 7t minus 1 over minus 1 plus c. Okay. Well, ideally, I want to simplify this by getting rid of minus 1. Okay. Now I can use this to evaluate the definite integral from 1 to 4 of the same thing. So I rewrite the answer there. Plus 7t minus 1 from 1 to 4. So now I have to just substitute the numbers. 3t is 12 plus, what is 4 to the power of 3/2? So I have to take the square root, that's 2, and raise it to the power of 3. That gives me 8, right? 8 times 2 over 3 plus 7 over 4. And so this is the upper limit. The lower limit is done similarly. I simplify a little bit and I get to this. I skipped one step, okay, in the simplification to save time. Questions? So you can see immediately the pattern in all these examples. The indefinite integral is a function with an additive constant. The indefinite integral. The definite integral is just a number. Okay. Now we are going to talk about the second part of the fundamental theorem of calculus in a very different light. We're going to have a real-life application of it, which is called the net change theorem. So let's write down our main object here. Okay. Or like this, f prime of x dx, the same thing. And we describe what this says in English, okay? Because both terms actually have a well-defined meaning. The quantity on the left contains f prime. Let me see if this works. No. Okay. The quantity on the left has f prime. And we know what f prime stands for. Okay. This f prime, if we think of t as time, okay, time variable, then f prime tells us how quickly f changes with time. So we can say that this is the rate of change. Okay. The quantity on the right compares f of b with f of a. We can think of, sorry, there are limits of integration here. So we start at time a and run the experiment or whatever we are dealing with here until time b. So the quantity on the right tells me the value at time b minus the value at time a. For instance, the height of my child this summer minus the height of my child last summer tells me by how much my child grew, right? So this is called, this has the meaning of net change. Net change. Or the total change that occurred to this physical quantity between time points A and B. So now we can say what this claims, what this claim is. The definite integral of the rate of change gives me the net change. And usually I'm interested in the net change. I want to know what's going to happen after a certain period of time if I know the law of change, the rate of change. So, example. Let's suppose that I have a quantity V of t is the volume of water in reservoir. Okay. And what is given is the time derivative of this quantity. Let's suppose it's given by t squared. And this is the rate of change, the rate at which the reservoir is filled. So this is basically, if I have a tap, it's filling up the reservoir. This is the intensity at which the water is put into the reservoir. So the units here would be, for instance, meters cubed per second. Okay, and the units here are meters cubed, the volume. Okay, so given this quantity, this is the law at which my tap works. It starts off by not doing much. T equals 0. It's closed. Then I open it, and gradually I put more and more water with larger and larger intensity. Okay, I want to know the total change in the volume of water between time 0 and time 5. Okay, or time 3. Find the change in the volume between t equals 0 and t equals 3. Okay, how do we do this? We go here. The rate of change, we integrate it, and it gives me the net change. So we integrate from 0 to 3, okay, and 3 seconds. Okay, it's important to not forget the units here, 3 seconds, because my intensity is measured with by meters cubed per second. So I need to integrate the rate, and this is what I'm doing. I substitute t squared here. This is our favorite integral. Okay, so I get t cubed over 3. So this is 9 meters cubed. Okay, so the total change in the level of water between time 0 and time 3 is 9 meters cubed. Yes. Questions? Okay, so I go from the rate of instantaneous change to the total change that occurs between 2 given moments of time. Okay. Next example. Let's suppose that C of t is the concentration of a chemical product. Measured by millimeter minus 3. Okay. So, given dc dt, for instance, 3 square root of t, this is the rate of change. The rate of a chemical reaction that influences the concentration of this product. Okay? Somehow, as a result of this reaction, the amount of C increases in time according to this rate. Find the net change between time equals 1 and time equals 4. Okay, so I start writing it out as usual from 1 to 4, and here I have 3 square root of t dt. All right. So I have to calculate t cubed, 4 to the power of 3 halves. Again, that's 8 minus 1, 14 millimeters minus 3. Okay. So that's by how much the concentration of product C changes as a result of this reaction. Questions? Next example is from biology, from population biology. So I'll give you an example of why is it that the quantity on the left is known and the quantity on the right is interesting but unknown. So for instance, in demography, we want to know by how much the population of a certain country will change in the next 20 years, right? And we cannot see the future, obviously, but we can make a prediction. How do we predict it? We look at the change, the rate of change of population, for instance, this year, last year, and the previous year. And we see that it doubles every year. It's a fake example, right? It doubles every year. So we know the law at which this function depends on t. Okay, we know that this is, for instance, a linear function of time. And now, given this information, we can extrapolate in the future. And we can claim that if the population continues to grow at the same increasing rate for the next 20 years, then we'll have that much of an increase. Okay? So the quantity on the left somehow can be sometimes extrapolated, estimated, or even calculated from first principles if we're talking about physics or chemistry. The quantity on the right is what we want to know. And all we need to do is integrate. So the example here is the population biology. It's kind of, for instance, the demography of bacteria. Okay, let's suppose that n of t is population of bacteria. And we know that the rate of change, the rate of growth of bacteria is 6t plus 2. Somehow I know this from the properties of these bacteria. And I want to know, so this would be seconds minus 1, okay? So I want to know find the net change in the population between time 0 and 1. I make my math easier here. Okay, so we integrate from 0 to 1 of this function dt. We'll find the antiderivative. And we evaluate it at the 2 time points. Okay, the antiderivative of 6t is 6 times t squared over 2. The antiderivative of 2 is 2t. So I have 3 plus 2 minus 0 is 5. Okay, so between in the duration of 1 second, the population of bacteria will change by 5 bacteria in this case. Okay. Questions? Question? Okay, you first and then. Okay.
First question, I was thinking that what if the problem said that the reservoir capped at a certain volume? How would you calculate the time?
Say again, if what?
If the reservoir capped at like maybe 13 meters cubed, how, and they ask you calculate the time at when it's capped, how would you do that?
You mean the reservoir is finite?
Yeah.
And the water starts overflowing?
Huh?
And the water starts overflowing?
Yeah, how would you know when the water overflows?
Very easy. We have to find the time at which the total volume exceeds the cap. So for instance, if we can solve this problem in the following way. I do it quickly to save time. So let's suppose we don't know what the eventual time is. So we put a variable t. Okay? We have a variable t here. What is the volume of water after time t capital? So I have t here. And the answer becomes t cubed over 3. Okay? By what time will this volume reach 13? I have to solve the equation. This equals 13. And then I find the time. What's 13 times 3? 39. So I found the time at which the volume of water reached the cap of 13. Okay? So that if I put a symbol here, not a number, that gives me the net change between time 0 and an unknown time t. So now it appears in this equation, and I can solve for it to find how long it takes. And it starts overflowing. Very good question. There was another question here?
Yeah,
yes?
Why did you write the arc secant or something like that?
Here?
Yeah.
Oh, second square, I'm sorry. Second square, that's the unit. Seconds.
Second.
Yeah, so maybe I should have just put. Not second square, second minus 1. So what is the unit of population change? The units of population itself are ones, because we don't measure them in kilos or in dollars, we just measure them in units. The change acquires a unit of time in the denominator. So the units here are just seconds minus 1. Very good question. Okay, so the last example is more involved and more interesting. So let's suppose that given is the velocity of a particle. V of t, say, is given by t squared minus 4 meters per second. So velocity is the rate of change of something. What is it the rate of change of? Position, right? So it's the same kind of problem. We have the rate of change, and we want to find the actual quantity, which is the position. Okay? But here it's more sophisticated. There are going to be two questions. Find the displacement for between times 1 and 3. Okay, so displacement is the difference in the position, so that's like the net change. Okay, and the second question is find the total distance traveled. So what's the difference, right? What's the difference? So here's an example where the two can be different. Let's suppose that I'm the particle, and I start at time equals 1. I start here, and I move. Okay, and I move back, and this is time equals 3. What's the displacement? 0. The distance traveled is non-zero because I went back and forth. So that's why they're different. Which tells me that I need to keep track of the direction of motion, whether I go back, and, forward or backward. And that's what we're going to do. So to solve this problem, we have to plot the velocity, because the sign of the velocity tells me the direction of motion. If the velocity is positive, I go forward. If the velocity is negative, I go backward. And all the information about the velocity is, of course, here. Okay? So I have to plot the function t squared minus 4. What does it look like? It's a parabola, right? Starts at minus 4. Where does it cross 0? So I can solve it. So t equals plus minus 2. And of course, I don't care about minus 2, because I care about the time interval between 0 and 3. So this is 2. Okay. I actually care only about time between 1 and 3. So at time equals 1, t equals 1, velocity is 1 minus 4 is minus 3, so I'm here. At 2, I'm at 0. And at 3, t equals 3, I am at 9 minus 4 is 5. Okay, 1, 2, 3, 4, 5. So this is my parabola. And I'm only interested in the time between 1 and 3. As you can see from this graph, the direction of motion changes. I start off going backward, then I stop at time equals 2, and then I travel forward. Okay, so but this I only care about this when I want to find the total distance traveled. To find the total displacement, I just follow the formula, and I'm not going to worry about the sign. So let's address the first question. The total displacement is given by the integral from 1 to 3 v of t dt. So I go from 1 to 3 t squared minus 4 dt. T cubed over 3 minus 4t is my antiderivative, evaluated at 1 and 3. Okay. So we have 27 over 3 minus 1/3 minus 12 plus 4 is equal to 26 over 3 minus 8. I'm doing it carefully so I get the precise number. 2/3 over meter. Okay. So my total displacement between seconds 1 and 3 is given by 2/3 of a meter. Not very far, right? Questions? So that answers only question number 1. So next we'll do question number 2. Let's do it here. The total distance traveled. What's it equal to? Well, I can write it in English. I'm going to say that it's the total distance traveled when we're going backward plus the total distance traveled when we're going forward, right? Because first we go backward according to that graph, and then we change direction and go forward. So equals total distance when going backward plus total distance when going forward. So to calculate this, I have to split my integral into 2 parts. The part corresponding to the backward motion plus the part corresponding to the forward motion. When does it change? It changes at 2 seconds, right? So my integral is going to consist of the part from 1 second to 2 seconds, and then from 2 seconds to 3 seconds. So I say this is equal to an integral from 1 to 2 seconds of v of t dt. Okay? And I'm going to put the absolute value here because I want the distance traveled. Between time equals 1 and 2, the velocity is negative. If I forget about the absolute value, I get a negative answer, which is not what I want. I want the total distance traveled. I don't care in which direction. Okay, so it has to be a positive number. Therefore, I put the absolute value. And then I add the distance traveled between seconds 2 and 3. And again, v of t dt. I'm going to put the absolute value here, even though I don't have to, because between seconds 2 and 3, I travel forward anyways, and it's a positive quantity. Questions about this? Question?
Could you like do it from like 1 to 3 and then just put like absolute value in the whole function?
No, for the following reason. When I did it from 1 to 3, and I obtained the answer, it's already too late. When I put the absolute value on this, it won't change. Think about my example with walking back, forward first and backward first, and backwards next. If I did it this way, I would get a 0 here, and I would not be able to recover the total distance traveled by taking the absolute value here. So this is because when I do it this way, without the absolute value, this gets subtracted, and that makes my answer too small. Okay, so I have to really add them together. So the first step here is really to split the time axis into intervals of motion where I don't change direction, positive motion and negative motion. And then I do each of them separately. Okay, and I do each of them with the absolute value. Was there another question? Okay, now from now on it's easy. Okay, so I go from 1 to 2, t minus 4 minus t squared dt, plus from 2 to 3, t squared minus 4 dt. See here, I flipped them. I did instead of t squared minus 4, I put 4 minus t squared because I needed the absolute value of a negative number. So this is v t, absolute value. See? And now I evaluate the antiderivative. And the antiderivatives are the same, except for the sign. Okay, here, this differs from this only by the minus sign. It used to be a negative quantity. I wanted to be positive, so I added a minus sign, which resulted in flipping, the order in which these terms appear. Okay. Now I have to calculate all the numbers. So the first one is 8 minus 8 thirds. So the answer is actually 4 meters. Okay. So the total distance traveled is 4 meters, and you have to compare it with the total displacement. This total displacement is less than a meter, because I first went backward and then I came all the way back. Okay, and overshoot by 2/3 of a meter. So the total distance traveled is normally larger than the displacement. When can I say that the total distance traveled is the same as the displacement? When I don't change direction. Either I go all the way backward or I travel forward all the time. In this case, the two are the same. Questions? Thank you very much.